Good morning. Today I'm going to talk about observations of ammonia absorption in Jupiter's atmosphere. Since ammonia vapor is condensable, its distribution serves as an important tracer of Jovian tropospheric meteorology. Current understanding of this distribution and its relationship to important parameters like aerosol opacity, cloud height, and circulation is provided by atmospheric retrieval models. These models use observations from major ground-based facilities or from spacecraft such as Juno. As a pro-am complement to these efforts, filter ratios have been used to enhance the contrast of 645 nanometer ammonia absorption using a small telescope. The technique and associated analysis software have been refined during two apparitions. I'll start by giving a bit more background on Jupiter's ammonia cycle, then I'll talk about the technique and the observations made during 2020 and 2021. Next, I'll show some highlights of the observations and analysis. Following up on the analysis, we'll look briefly at the potential for this data to be used in atmospheric models. Then I'll present what I found to be lessons learned and best practices and wrap up with a summary. New microwave and mid-infrared observations, along with models, reveal much about Jupiter's ammonia cycle deep in the atmosphere. For example, Yeo et al. 2020 showed the average of ammonia abundance retrieved by the Juno microwave radiometer to a depth of 100 bars. Major deep-rooted upwelling is seen in the equatorial zone, and significant depletion is seen in the north equatorial belt. In addition, there are numerous other latitude-dependent features, including smaller-scale convection effects. On the right, we see an optical image and the ammonia abundance at the 500 millibar level from Fletcher et al. 2016. Note how the ammonia abundance and visual features have a complex relationship. The interest, breadth of techniques and importance of the study of Jovian ammonia prompts my investigation, which asks the question, can observations of ammonia in the top 1 bar of the atmosphere be used to infer deeper processes? Moving on to the ammonia absorption imaging technique, we see a flow chart from observation to data products. This approach was detailed last year at this conference, at the EPSC meeting in September, and at the fall AGU meeting. Technique rests on the premise that the pixel by pixel ammonia absorption can be obtained by dividing an in-band image by the average of adjacent continuum images. This creates what I call a continuum divided absorption image. The resulting products of the process include disk integrated absorption, meridional absorption profiles, and resolved absorption images. Assuming a canonical disk integrated ammonia equivalent width, the equivalent width can be computed for each pixel. Here's what the processing pipeline looks like in a bit more detail. FITS images, typically from a CCD camera, or video files from a CMOS camera can be used. Standard calibrations are applied and initial stacking is carried out. Disk integrated photometry doesn't require image navigation, so it can be performed at this point in the pipeline. Once navigated, images are again stacked, compensating for planetary rotation as necessary. The image ratio computation is carried out on mapped images that have been rotationally aligned. But before the ratio is computed, the images are brightness equalized in order to simplify accounting for differences in filter throughput. For detailed study, the images are converted into cylindrical projection maps, and only the central 45 degrees are analyzed. This avoids more severe limb darkening effects on the data. The observations were carried out from the Authors Observatory in Denver, Colorado. 2 imaging configurations were used, both with the Celestron 11 telescope. The first configuration used Lucky imaging with a CMOS camera to detect discrete ammonia absorption features. The CMOS data were not photometrically analyzed. The second configuration captured images with a CCD camera, and a photometric analysis was performed. A total of 40 observing sessions were conducted in 2020 and 21. And of those, 1 was discarded as unusable, leaving 39 sessions for analysis. This slide shows the observational coverage along with Juno Perijove data. Note that during July 2020, CMOS observations overlap with longitudes observed by PJ28. Similarly, in September 2020, CMOS and CCD observations are obtained adjacent to PJ29, and in 2021, the best adjacent observations occurred in October at PJ37. While somewhat coincident with PJ36, The System 1 longitude range of 140 to 180 degrees was observed multiple times in close consecutive observations in September and October. This allows for observing the evolution of features in the equatorial zone. I'll also point out that the quality of 2021 observations was improved over those of 2020. The 2021 observations always were flat fielded and used both blue side and red side continuum reference images, whereas in 2020, some of the observations lacked flat fields and only used a red side continuum reference. So now we'll move into the highlights of the observations and analysis, and we'll look at the kinds of features that are seen. The upper left map is the one that shows ammonia absorption, where brighter indicates higher absorption. The context maps provided include methane, near ultraviolet, visual color, reflectivity, and color slope, where brighter means redder. In these plots, the overlaid contours show the estimated ammonia absorption equivalent width. Large-scale features are seen, including the reduced absorption in the North Equatorial Belt, the equatorial zone enhancement, and depletion around the Great Red Spot. Note that the relationship between visual features and ammonia absorption is complex. For instance, there's a depletion clearly correlated with the Great Red Spot. However, the Northern Equatorial Zone and North Equatorial Belt region is uniformly dark in the near ultraviolet, but this region overlaps enhanced and reduced ammonia absorption regions. Now we zoom in a little bit more on the equatorial zone and the North Equatorial Belt. We see significant longitudinal structure, and that's especially true in the ammonia absorption enhancements in proximity to plumes and dark features. Bright plumes represent high clouds, and dark features are clearer and let us look deeper into the atmosphere. These are areas of upwelling and downdraft, most likely associated with a global Rossby wave. Typically, ammonia abundances are depleted in the dark features and enhanced in the bright plumes. Unfortunately, the ammonia absorption alone can't tell the story of abundance without better knowledge of the scattering path and aerosol properties. Now we look a little bit more detail around the Great Red Spot at 3 different epochs in 2021. Reduced ammonia absorption is consistent across the 3 observations. However, there are offsets seen in the estimated equivalent widths, likely due to systematic calibration errors. This depletion is likely due to the high altitude scattering layer, and it's also been noted by Typho et al. 2018 in spectroscopic measurements. Note that the depletion appears shifted towards the southeast. Fletcher et al. In 2016 found a gradient from enhanced to depleted ammonia mole fraction at 440 millibars from the north to the south across the Great Red Spot in mid-infrared data. Again, the absorption observations can't be connected to the abundance observations without further knowledge of aerosol scattering and cloud height. Now we look a little bit more at meridional profiles of ammonia absorption equivalent width. The top chart shows the zonal profile, the meridional profiles, and the bottom chart shows zonal profiles. The solid blue line represents the present work averaged over 2020 and 2021 CMOS observations, with the shaded envelope being the 1 sigma variation. Note the smoothness of the zonal profiles compared to the meridional profiles. The current work generally matches the spectroscopic data of Typho et al. 2018, which is shown as blue dots. However, there are differences in the details, such as the northern equatorial zone enhanced absorption that's seen more prominently in this work. The green line and envelope show the ammonia abundance at 440 millibars from Fletcher et al. 2016, along with the standard deviation from their data. The abundance contrasts are higher than those in the absorption observations. In addition, the depletion seen in the South Equatorial Belt is not seen in the optical observations of absorption either in this work or that of Typho et al. These differences suggest significant deviations due to cloud top heights and scattering properties as mentioned above, and perhaps there are temporal variations that are also occurring. Now we move into modeling and what potential there is for these observations to contribute to modeling. What we're looking at here is a single scatter plot of several that have been created and analyzed. We're looking at methane brightness versus ammonia equivalent width for different meridional bands. The thing we're looking for here are discriminating factors that exist between different visible features. High brightness in methane, for instance, indicates higher cloud tops, which leads to less absorption. Thus, the great red spot shows up as a high reflecting layer with low ammonia absorption and is seen as a red tail extending to the upper left. The equatorial zone, which is plotted in green and purple, exhibits high methane brightness, but also a wide range of ammonia equivalent widths. This suggests a range of features related to ammonia abundance or cloud height. The north equatorial belt shows uniformly low methane brightness, indicating deeper cloud tops, but also shows the lowest ammonia absorption. This would support an actual depletion in ammonia abundance since the scattering length is relatively large. The scatter plot analysis suggests that a simple reflecting layer model might provide meaningful first-order retrievals of atmospheric properties. Reflecting layer models are the simplest form of radiative transfer model. They're straightforward to implement and can provide first-order insight into parameters of interest. The model shown here is from Mendicoa 2012, and it uses near-ultraviolet, red, green, blue, and methane filtered images to retrieve reflectivity and cloud top pressure. Models like this have also been used for assessment of amateur images, including those of wide spot. The goal in 2022 will be to retrieve reflectivity, cloud top pressure, and add retrieval of ammonia abundance. Filter selection needs to be tuned more specifically to molecular bands of methane and ammonia, along with appropriate continuum bands for this to be successful. Choosing the best combination of filters is really going to be key to this retrieval. Narrowing the wavelength range to a small region in the red simplifies retrieval at the expense of spectral coverage of reflectivity. This can be accomplished with filters placed roughly at 620, 632, 647, and 656 nanometers. The effective absorption cross-section for these filters, K effective, shows how some are very sensitive to methane absorption, and those with minimal methane absorption are suited to continuum or ammonia measurements. Alternative filters are also shown, though each has drawbacks. As a bare minimum, the 647 and 656 filters will provide qualitatively useful ammonia observations. Now I'd like to talk a little bit about best practices, the things I've learned along the way over the past 2 years. First of all, there's kind of general best practices that many people are going to be familiar with in doing planetary observations. You want to maximize signal to noise. You want to apply your basic calibrations, biases, darks, flat fields. And if the elapsed time during an imaging session exceeds about 2 minutes, you need to correct for planetary rotation before even the initial stacking of the images. So there are some additional best practices specific to ammonia observations. That includes making sure the camera gain and gamma are set to linear. This is really important to get the relative ammonia absorption on a linear scale. No sharpening techniques should be applied. They often result in artifacts that are unphysical or not realistic representations of the absorption. A session to produce an ammonia image shouldn't be longer than about 20 minutes. This ensures that you don't have any rotational effects that results in limb darkening, propagating artifacts into your analysis. In-band and continuum observations should have central times that are within 5 minutes of each other. It's best to obtain continuum reference images on both the red and blue sides of the central absorption band at 645 nanometers. And the continuum references have to avoid other absorption bands as much as possible, such as the methane band at 620 nanometers. However, measurement of that band deliberately can be really useful for establishing cloud height. Now I'd like to move into a little bit of a tutorial, couple slides here, just showing how I actually create the continuum divided images. The programs I use are WinJupos and Maxim DL, but others are available. And it probably doesn't matter too much which image processing program you use. So the first step is to take your images in your red and blue continuum and your center image and create an RGB derotated image in Winju pose. This means that you've gotten all of your alignment set up rotationally between these images, and they're at a single epoch. You take that image then, move it into MaximDL or your favorite image processing software, and you white balance the image. You want to select a large portion of Jupiter for this, but you don't want to include any artifacts such as the limb edge that you can see at the right in this particular image. And of course, that's due to rotational offsets. When you white balance the image, what you're doing is you are brightness equalizing the 3 channels, your 2 continuum channels and your ammonia channel. Then you split the tricolor, the white balance tricolor image, and you can compute your ratios in MaximDL. What you do is you divide the green image, which is your ammonia absorption image, by your red continuum, and you also divide it by your blue continuum. You do this separately, so you end up with 2 images. One is a blue divided image and one is a red divided image. Then you combine these 2 images to get that average continuum divided absorption image. It's best to combine these as an average and to do it in IEEE floating point format, because the numbers you're going to get are going to be very small. They're going to be in the range of maybe 0.5 to 2. So you need to have that floating point there. And then as a final step, to stretch this for a, so you can look at it visually and you can save it as a PNG file. I typically stretch the images from 0.9 to 1.1 and save that as a 16-bit PNG image. That's pretty good to look at the contrasts there. You don't end up with any saturation in terms of high and low points on ammonia absorption, and you can really see the features there. And the final best practice is going to be data sharing. After 2 years, I feel comfortable that I've validated this approach. So now I'm going to start to share my data on public websites like the Planetary Virtual Observatory and Laboratory, PVOL, and ALPO Japan. I plan on uploading not just the ammonia continuum divided image, but also the source absorption and source continuum images. That makes it complete and allows other people to actually take those images and do those ratios and see if they come up with the same sorts of things that I'm seeing. The minimum metadata that needs to be included is the central time of the observation and the filter bands, including the wavelength and width. And of course, there's tradition to add a lot of other things like the instrument, focal length, air mass, central meridian location, etc. And those can be added as annotations to the images. Sharing this data will allow a wide range of amateurs to evaluate the observations and look at them and maybe even use them. It's straightforward to image the ammonia absorption on Jupiter, and I'd love to see other amateurs take a shot at it. So in conclusion, this paper has highlighted 2 years of continuum divided ammonia absorption imaging on Jupiter. The method shows detail inaccessible with other imaging techniques. Simple atmospheric retrieval model will be tested during the 2022 apparition, and curious amateurs are encouraged to try ammonia imaging for themselves. Here I've provided some of the key part numbers for the in-band continuum, red continuum, which is a little bit harder, blue continuum, which is a little bit harder to obtain than the red continuum, which is a standard H alpha filter, and also the 620 band that can be used for methane cloud head measurements. So good luck, and I encourage you to give this a shot if you're interested. Thank you.
Questions for Stephen?
This is Wayne Green.
Wayne, if you can hear me, you're very faint on my computer.
Let's try this again. This is Wayne again. Are you actively seeking collaborators?
I am. Yes, I'm actively seeking collaborators, and I encourage people to either post publicly or to reach out to me directly, and I can assist with questions you have, parts, the way I've put things together in more detail. So definitely.
Right, thank you. Other questions? Are there any questions online? Nope. Bob?
Hi, Steve. I may have misunderstood you, but it sounded as if you said that you did not do photometric analysis of the lucky imaging images. Could you explain what went wrong?
Yeah, well, I will say that when I heard myself say that, it was a little bit confusing. What I didn't do was disk integrated photometric analysis on the CMOS images, on the lucky images, because I did not have photometric references that I could use. With the wider field of view of the CCD chip, I typically used some of the Galilean moons for photometric calibration, disk integrated photometric calibration. For the relative photometry between the blue and red continua and the in-band image, that can be done without an external reference. So it's relative photometry when you're looking at just the image details themselves. Does that help explain it?
Yes, thank you. That makes sense.
Okay, I don't think there are any more questions. So thank you again, Stephen.
Thank you.